Okay, so we're going to skip over these sections quickly because the structure is very similar to what we saw above. If you want to have estimates, approximations to the sampling distribution of the variance, there is a math formula based on the chi-square distribution. That's the analytical approximation based on the scale factor. And if you plot that approximation, so this is the true sampling distribution of the variance, and if you generate a chi-squared model for it, that's the analytical approximation, you get a very good fit. Okay, so that's thanks to math, thanks to the analytical approximation. And again, if you don't want to do math, you can do this with the bootstrap method to obtain not as good an approximation, but you get the general shape, right? The fact that it's a little bit off is because we wanted this distribution, the true distribution should be centered at 100, and the bootstrap approximation is centered at 118. But we still get a good approximation for the standard error of this distribution. Okay, and similarly, if we want to analyze the sampling distribution of the difference between means, we can come up with a math formula based on the normal approximation. You know, this is what the central limit theorem tells us, and instead of using a normal approximation, we're going to use the t-distribution. Skipping over this complicated math here. And what do you get? I'm going to define this function. Okay, so we have to look at a particular example, the electricity prices. So the estimate is 3, right? So the estimate of the difference between the population, the mean of the west end and the east end prices is 3. But we compute all these quantities, and we are able to obtain an approximation using a t-distribution for what the real variability of the estimate. So we know we computed 3 as our estimate, but we are able to know the variability of the estimates. So we know that our estimate is really a 2 to 4. You know, we obtained the point estimate, so the actual guess about what is the difference between the population mean is 3, but really it's anywhere between 2 and 4. And similarly, instead of using math, we can use the bootstrap. So this is a little bit different because we have to bootstrap the mean from the two populations separately, and then we subtract the two distribution to obtain a bootstrap approximation. So you see, we get the estimate 3 and the variability of our estimate around 3. Okay, so these are the so the theme is repeating 3 times now for the sample mean, for the sample variance, and for the difference between means. We see that we can use math, analytical approximations, or we can use the bootstrap to quantify our uncertainty, the uncertainty in our estimates. So you can read the details in the book, just because the videos are getting long already. Okay, the last sections in this the last subsections fill in some details. Okay, so remember the formula for the sample variance. It uses the 1 over n minus 1. But what happens if you use 1 over n? You know, we've been saying that repeatedly, just use n minus 1, use n minus 1. So if someone wanted to use 1 over n, so this estimator is exactly like the sample variance, but instead of dividing by n minus 1, we divide by n. So let's see what happens. You know, it kind of looks okay, but if we compare it, we'll see that we're actually underestimating the sample variance. So if we use the real, if we use the formula with n minus 1, on average, we get very close to the true population variance. But if we use 1 over n, then we're going to underestimate. And remember that the average of the sampling distribution, unbiased estimator should on average hit its target. And this is true for the variance, you know, the estimator we've been using all along. If you use 1 over n, which is this estimator here, S2 tilde, then we're going to consistently underestimate. So the math term for this is that it's a biased estimator. So that's why we do the n minus 1. The name for this is called the Bessel's corrections. Bessel's correction. And I've shown you the simulation, but you can do the math. So there's a bunch of problems, problem 3.1 and problem 3.2, where you can go through the math steps to show that this is the estimator you want to use when you want to estimate the sample variance. Okay, there are some other topics that you need to know about. Here's a little discussion, like this whole idea of degrees of freedom. And there's another concept which will play an important role in the next section, but just a little foreshadowing here. Any random variable, if you multiply it by a constant and you add a shift, horizontal shift, you get a new random variable y that has the same distribution but wider and shifted. So this is called the location scale transform. And that's very useful. So here is the inverse of that. So if you know the variable y, you can subtract the location, so shift it back to the to 0 and divide by the scale. So this transformation is useful for both the sample mean, the sample variance, and the difference between means. So for historical reasons, when we build models for sampling distributions, instead of saying, oh, this is one that's located here and this is its spread, we want to take away that information. We say, I want it to be standard spread and standard location always at 0. So these transformations, instead of using the model with a custom location and custom scale, we can use this called the standard t-distribution. It has location 0 and scale 1. And similarly for the chi-squared distribution, we don't want to have a custom scale. We want to have the scale 1. So these transformations, this one, I guess it's the same, and this one are, this is purely for computation reasons, allow us to use the standardized distributions. Okay? Historically, the people used to print on paper these tables of distributions and do probability calculations by looking up. They say, oh, I need to know the t-distribution for this number. When you're using standardized distributions, it's much easier. Like you can just print all the values and then look up on paper. So we'll see these quantities again in the next section, the pivotal quantities. Okay, and that's it. Like this is all foreshadowing. So the remainder of the section I'm gonna skip because we'll do a better job in later sections. But just to a little foreshadowing, when you build an approximation, so this is going back to the Apple weights. We computed the sample mean, we computed the estimated standard deviation, and we can then say useful stuff about, okay, so we know the sample mean is 202.6, but by calculating the standard error, we know how to quantify the errors in our estimate. And the red things here are contain 90% or yeah. So your estimate for the average population mean, you don't know what the sample mean is for the population of Apple weights, but you can say for sure that it's you can build this interval from the lower bound to the upper bound that contains 90%. Your best guess is that it's somewhere between here and here. Okay, and another application in hypothesis testing will use a different type of reasoning. If you know the sampling distribution, you can look at particular samples and say this sample, so the blue line here describes the sampling distribution of the kombucha volumes of the mean when it's working correctly. Like we know that it's supposed to be, the average is supposed to be 1 liter on average. And you get a sample with a 999. This seems to be a normal sample, right? It's within the expected. We expect this variability for the samples, and we see the sample from batch 01 falls here in this distribution, so it seems to be a normal sample. This sample, however, it seems to be really outside of the range of normally expected samples. So there's maybe something wrong with this sample, like it says really low mean. So we better check the production line. We're put like there's something wrong with batch 06. Okay, yada yada yada. Okay, last point. We talked about analytical approximations and bootstrap. They're both. These are two alternatives. Like I want you to know both ways, but in practice you're going to use one or the other. And the difference is when you can use one or the other depends on the population. So the normal approximation, so the analytical approximation, the chi-square, the t-distribution, all of these only work when the population is normally distributed. So they're very powerful. They, statisticians develop custom math formulas that help you find the sampling distribution, approximate using, we saw that the curves were really good, but they depend on a normally distributed population. So if you try to use the t-distribution or the chi-square distribution for an exponential population or a uniform, you might not get they will be less good. In contrast, the bootstrap is more general purpose. We saw that the accuracy was a little bit less, but it doesn't make any assumption about the population. So it's like a general purpose method. So here is a little decision tree. Which method should use the bootstrap or an analytical approximation? When the population is normal, you can use either the bootstrap or the analytical approximation. Like they both work. If the sample size is not big, like think like 7, earlier, then use the analytical approximation because it's custom designed for small samples. Like the t-distribution is like the best in line approximation for it's custom designed for small samples from a normal population. So this is when you use the t-distribution or the chi-square. On the other hand, if the population is not normal, then bootstrap, you can still use it. You can't use any analytical approximation. They're not valid. They assume the population is normal, so you cannot use, okay, you just use the bootstrap. In the middle, if you have like a little normal distribution, the population is normal, but like a little bit skewed or a little bit wider than normal, then you can use the bootstrap for sure, but analytical approximations, they kind of work. So this is unfortunately how statistics works. I taught you the math, I taught you the computational approach, but the middle ground is where most real-world scenarios are. It's this is the easy case. When the population is normal, you know what to do. When it's kind of normal, then you can still use analytical approximations, but it's a bit like using the tool that's meant for one task, but you're using it in a different task. So not sure, not guaranteed to work. Okay, and this is it. We have reached the end of the section. Again, reminder, if you go to this link, there is a notebook with the exercises. Open recent. So let me show you. I'll send you the direct link, but the exercises 31 estimators. See, there are 15 exercises, and I've already set it up all the way to the end. Try this out. So while reading, I want you to try the exercises at the same time. All right? Just filling water the gaps here. If you want to know the solutions to this exercise, you have to go in the subfolder solutions, and you'll find all the solutions here. But please don't check the solutions. Try on your own first. All right? Good luck. I know this was a lot of stuff. You have to trust me on this one. This section 3.1, we're done. Like all the math and the difficulty of explaining sampling distributions, approximating them, bootstrap, analytical formulas, all of this stuff. I know it's very dense, it's intense stuff. But if you manage to get through this 60 pages, how long is it? 67 pages, I can tell you all of chapter 3 will be super easy. From here on, there will be no new math. All we're going to do is take the analytical approximation, the bootstrap, we're just going to do applications. We say, oh, I want confidence interval. We're going to cut off chunks from the sampling distribution, and you compute the confidence. Hypothesis testing, we're going to, under a hypothesis, we're going to generate the sampling distribution, then compute p-values by saying, oh, is this likely or unlikely to occur under this distribution? So essentially, we're done. All the difficult stuff in chapter 3, we're done at this point. So good luck reading it. Email me if anything, and see you in a few weeks, where I'll send the section 3.2 and the hypothesis stuff later this month. All right? Ciao.